stuff.
Hello and welcome to another episode of Making Stuff Look Good in Video Games. Dishonored 2 is a pretty dope looking game. It also has some of the most clever level design of anything I played last year. The game's striking visuals and cunning design are best represented by the 7th mission, A Crack in the Slab. It's hard to say whether the Outsider's timepiece is more visually or mechanically interesting. Any way you cut it though, the devs pulled off something super cool. So let's break down the effect and see if we can recreate something similar in Unity. At any point we can look through the timepiece and see into the other timeline. We know it's more than just discolorations and distortions because there are plenty of differences such as varied meshes and NPCs that are only visible in one timeline or the other. So I suspect we're seeing two different scenes being rendered. The timeline the player is not in is rendered to an off-screen buffer. Next, the scene is rendered normally to the screen. And finally we render the timepiece itself, which samples from the first steps buffer to create the illusion of looking between the two timelines. As for where the two scenes' contents are actually positioned, my suspicion is that this came down more to the physics and mechanical implementation more so than the visuals. From a graphics perspective, there's not a whole lot of difference between having two scenes worth of geometry stacked right on top of each other versus physically separating them. Either you'll have to make your cameras only render the geometry they should see, or you'll have to position the cameras in both scenes such that their view is the same. The timepiece itself is doing a bit more than just sampling screen positions into the off-screen target. It appears to be a refractive piece of glass and is likely using a normal map to distort the sampled image. It's also probably using some variation of a PBR shader with some colored specular highlights, and I think it might be using the roughness map to dynamically blur the sampled image, or possibly just blend between a crisp and a blurred result. This stuff all gets a bit more complicated and out of scope for what I'm hoping to cover today, so we'll just cover the refraction, which is really the cooler part of the effect. Aside from the timepiece and its fancy rendering, there's the effect of jumping between the two timelines when the timepiece is activated. There's a lot going on here, but it's nothing too complicated. The feeling of warping comes from animating all the camera's field of view, increasing with some fall off and then snapping back. It looks as if the player's held items move closer to the view as the field of view increases. This gives the illusion of the object staying the same distance away but stretching outwards. As the field of view stretches out, the screen color desaturates. This makes the transition when we eventually swap cameras less noticeable because the two scenes look much more similar in grayscale than they do in color. There is also some blurring going around with a bias towards the corners, but it seems to be inconsistent with each use of the timepiece. It might be randomized in some way, or maybe it's just some weird byproduct of changing the field of view with motion blurring enabled. I'll be foregoing this part of the effect in favor of a more traditional vignetting, which gives a similar tunneling effect. After we swap cameras, all the stretching and desaturation snaps back very quickly, like in less than 100 milliseconds it seems. A particle system of floating white sparks is spawned at the player location, and a short-lived screen effect with some distortions plays. I'm going to gloss over the post-warp effects, but covering the refraction on the timepiece will give you a good idea of how you might implement the screen effect seen here. Okay, let's jump into Unity and make some stuff. There's a lot of flexibility in how you set up your scene for this effect, so here's how I went about it. In one scene, I have the regular level geometry, and all of that has its layer set to Universe A. We then build Universe B in a separate scene. This lets us keep the light maps for the two scenes separate, which will be helpful for more complex scenes. Again, all of the geometry here is placed on its own layer called Universe B. We'll add both scenes to the build settings, and in a small script in Universe A, we'll load Universe B additively when the game starts. The player will actually have two cameras attached to them, one which has its cull flag set to only see Universe A, and another that only sees Universe B. If we played right now, both scenes are going to be rendered, and which one we see is dependent on their depth. Note this depth value on Unity's cameras has no relation to the Z buffer. It actually is just a floating point value used to sort which order cameras should render in from low to high. If we were going to swap between universes without being able to spy into the other, we could just set only one camera to be active at a time. But we're going to get a bit fancier than that, so let's get set up to render our timepiece. I made a small script called the Twin Camera Controller. When the game starts, it creates a render texture that is the size of the screen and sets it as a global texture available to shaders. We'll set the hidden camera's render target to this new render texture. The hidden camera is a universe we aren't currently in, so it will start as the camera for Universe B. When we want to swap between universes, we'll have the active camera set its target to the hidden camera's target, and the hidden camera set its target to null, which means it will render to the screen. Then we'll swap the references to which camera's which, so that the next time we call our swap cameras function, we'll switch back from universe B to universe A. In our game, if we call swap cameras, we'll instantly switch from one universe to the other. Meanwhile, the hidden camera will actually be rendering off screen for use in shader. So now we'll need our magic object that can spy between universes. I made this janky looking model of a handheld mirror, but you can use whatever you want here. The most basic implementation of our magic item shader would be one which computes screen coordinates for each pixel and then uses those screen coordinates to sample the render texture we set up earlier. So let's start with that. We'll need an interpolator to store our screen position in as it goes from the vertex shader to the fragment, but notice that I'm using a float 3, which is one more dimension than you might expect to see considering we just need a 2D screen coordinate. The reason is explained here in our vert function. After our vertex position has been multiplied by the MVP matrix, it's in clip space coordinates, which is in the range -1 to 1. Now before we remap the point by adding 1 and multiplying by 1/2, we first need to account for perspective distortion. For our usual fragment position, the GPU will divide out the W component of the vertex position for us, but for our own coordinate, we'll need to divide out the W component ourselves. The issue is, if we perform this perspective correction before interpolation, our values get all jacked up. They'll look kind of correct, but at grazing angles and points close to the camera in particular won't look quite right. So we actually want to perform the perspective correction after interpolation. This is why we use a float 3 instead of just a float 2. We'll store the W component in the third channel so that we can use it in the frag function. Now we can safely remap our values from -1, 1 to 0, 1. As a little optimization, you can still do the remapping in the vertex shader, you just have to be crafty. We know that this value is going to have the W component divided out eventually, so adding 1 wouldn't be correct. So what number could we add will be 1 after the W component gets divided out? The W component! So here's the final line in the vertex shader and the line performing the perspective correction in the fragment shader. If we use this screen coordinate to sample our render texture, we get the simple base for our effect. If I hide the metal part of the mesh, you can see our efforts to have aligned cameras viewing identical geometry have paid off, and there's a seamless transition from one universe to the next. The glass on my mirror is broken up a bit, and I've gone one step further and made a smashed glass normal map that should make for some pretty interesting refractions, so let's tackle that next. I'm going to gloss over normal mapping code here and possibly cover it more in depth in a later video, but these chunks of code are pretty standard and you can find them in various flavors and methods of them on different tutorial sites and different rendering forums. The end result of normal mapping code is usually a normal vector in world space visualized here on the mirror's surface. But before we can use these normals to distort how we sample the render texture, we'll want to transform them into view space. When we visualize the view space normals, they appear consistently colored as we move about the scene instead of changing drastically with our world space rotation. Now we can use the normals X and Y components multiplied by some value to create a refractive effect on our glass. At this point you might be asking a very important question. Isn't rendering the entire scene twice, like, really taxing? The answer is of course yes. Drawing the whole world twice basically means doubling your base frame time. So here's a funny little hack we can do to cut down on all that overdraw. This episode's already going to go way over on time, so I'll point you to the code on GitHub for implementation details and just give the high level description. We're only seeing a small portion of the other universe, that is, the area covered by our mirror, but we're drawing the entire screen's worth of pixels. What if we could only draw a small area around our mirror that we'll need to sample our refractive glass from? When we render the opposite universe, instead of clearing the Z buffer to the maximum distance as you typically would in a frame, we'll instead clear to the minimum Z value such that everything would be culled. Then, before anything else draws, an invisible quad is drawn. This quad is set to always pass the Z test, and regardless of where it sits physically in 3 space, it always writes the maximum depth value. It's almost like we're punching a hole through which the rest of the scene will draw. We can see the net effect visualized in the frame debugger, where pixels outside of our special depth quad are culled and only a much smaller portion of the screen is drawn. With that optimization in, we've just about covered everything. We can jump between universes, and our magic mirror lets us peek into the opposite universe. But before we wrap up, let's make the transition between universes a little bit more satisfying. We'll basically just animate all those things I mentioned earlier. There's a lot of freedom in how you implement this. I just used a coroutine and half a dozen animation curves to control the various values. To reiterate, we'll animate all of the camera's field of view, a full screen desaturation, a vignette effect, and the mirror's position relative to the player. And then there's one extra thing you might want to animate that affects both the visuals and the mechanics, the global time scale. It creates a feeling of time crawling to a halt before jolting back to its regular speed. Most of my curves have a shape like this, with the value easing toward its target and then rapidly moving back to the default value, but with a little bounce past the resting value. This little bounce is especially noticeable in the field of view and creates a wobbling sensation after the player changes universes. And lastly, never underestimate the power of adding a good sound effect to your game to make everything just a little bit more compelling. The sample project and source code used in this episode are available on my GitHub. I hope you enjoyed this episode of Making Stuff Look Good. If you want to support the show, you can chip in $1 or $2 on Patreon for each new video. Thank you to all my patrons for your continued support. You rock. Hey, do you like video game development? Do you like podcasts? Well, if you answered yes to one or both of those questions, then you should check out the Debug Log. It's a podcast by devs for devs. I work with a few of the hosts and can vouch for them being equal parts knowledgeable and entertaining. This week's cast features yours truly, so if you want to listen to me babble on about shaders and junk for like 45 minutes, you can totally go do that. You can find the Debug Log on iTunes or at its home on thedebuglog.com. And as always, thank you all for watching. Keep on making those video games.